Get started. Okay, hi everyone. Welcome to the civil seminar this week. So we are very pleased to have Professor Simon Laflamme with us today. I just want to give you a very brief introduction first. Professor Laflamme is a Waldo Wagner Professor in the Civil Engineering and the Department of Civil Construction and Environmental Engineering at Iowa State University. He also holds a courtesy appointment in the Department of Electrical and Computer Engineering. Simon has received his PhD in Structures and Materials from MIT in 2011 and has received the Early Achievement in Research Award from Iowa State in 2017. He has been very active in research, and it has attracted over $5 million of research funding from different agencies. He's also in the editorial board of high-profile journals like Measurement Science and Technology, Sensors, among others. He has many publications, over 170 papers published in the areas of structural health monitoring, smart structures and systems, and structural control. So it's a great pleasure to have Simon with us today. And without any hesitation, I give the mic to Simon to go ahead with the presentation. Thank you, Mike. Thank you, Simon.
Thank you for this nice introduction. So I suppose I have an hour for this talk, right? Total, like, so what, 2:30?
Yeah, usually we go with 45 to 50 minutes, and then we have about 5 to 10 minutes for Q&A.
I will try to be on track.
Sure,
I also sent you the slides, so while I talk, if you want to forward them, it's up to you if students want to.
Okay, you can share the slide, but I can also share it for you if you want to.
If you can allow me to share the screen, yeah, that might be easier because I have some videos.
Sure.
I mean, well, if the audience is, some of you want to volunteer and put your cams on, that's much easier than talking to a black screen or talking to myself, at least in the screen.
Yeah, the problem with that, Simon, is that when everybody turns on the camera, then we might have some technical issues. But we can try. But we have had that problem before. So Simon, did you send me the slide in PDF or
I sent you a PDF, but yeah. I think you can enable sharing screen though. On the bottom, yes. On the bottom, you have this little share screen button, and next to it, a little.
Yeah, I just did it. Yes.
Okay.
You should be able to share it. Yes.
All right.
Perfect.
And the only reason why I asked for, well, there's many reasons, but for the video is this control thing, right? Some feedback. Some people like to make jokes, but I like to do some humor, but nobody laugh, nobody smile. It's like, you don't know.
I know it's tough. But,
although I must tell you, it's hard to make humor with high rate systems, but I can try my best.
Thank you for this.
Okay, well, I get started then. So my group here at Iowa State do work in both health monitoring and control. I won't talk much about these two topics individually, but briefly, control, we like to design, imagine new devices for reducing vibration in buildings and algorithms for feedback control. In terms of health monitoring, we do work in sensor development mainly. So we invented this sensing skin that we deploy on structure. So we did a lot of work in that. And of course, the algorithms that link signal to decision making. And that's important for today because what we've done is kind of merge these two topics together to address this challenge called high rate structural health monitoring or high rate state estimation. This high rate thing is a new topic. It's a niche, if you want, in the whole realm of state estimation field that was pioneered by us and the Air Force Research Lab a few years ago, and additional colleagues start to get into this, like Dr. Sedu that you probably know at Western. So that's how I ended up, getting this invitation here. So again, thank you for having me here. It's quite a privilege to talk about this kind of new topic here. So before I start in this whole definition, let me show you a video. And you see the video, right? Good. So that's a high rate system right there. It's a piece of weaponry going through three different concrete walls. And I'm a civil engineer. Of course, look at this, like, oh no, the walls, right? So we're not trying to monitor the concrete here. Instead, we're trying to monitor the device itself, so the missile that goes through those walls. So one of the challenges, to give an example through this slide, is do we have enough time to estimate the health of the weaponry between two targets and make a decision? For example, once you go through a wall, do we have enough time to say, hey, that's damaged. It shouldn't go further, so do not detonate, right? So in terms of war application, that's what would save lives by not detonating next to schools and wedding and so on, or what they call smart detonation. So that's one of the key examples that we like to give when we talk about a high rate system, right? That kind of resonates with people. But it's not just about missiles. In terms of civil engineering, and I suppose that most of you are, that's one of here the main concerns we have: blast mitigation. And I've seen, in terms of control theory, some people, some colleagues have come up with great ideas. For example, a balloon that could be inflated when there's a blast. So there's a blast that comes, you inflate this balloon that absorbs some of the energy coming to the building. So that's good, that could work. The problem is we don't have time right now to do that. We just need time to understand there's a blast coming to you, quantify it, make a decision, and tell your system inflate, and also inflate the system, right? So that's kind of a high rate event. In order to be able to enable this, that we need to be able to develop those sensors, algorithms, decision systems, and name it. So we do work on algorithms on our side. And here, I put 3 bullet points of quantified examples for TNT 10 kilogram, only 0.3 milliseconds per meter. Hypersonic vehicles, that's one of the dreams, especially in the US, we're trying to work on that. Hypersonic is at least Mach 5 speed, and at that speed, we're talking about 1.5 kilometers per second. So you blink, you've been through a lot of speed. So imagine that these are passenger vehicles. Well, you have to rely on those feedback systems to save life and maintain the operation of your aircraft. And also, it comes with challenge with this sampling rate, right? If you want to make decisions, suppose you have this super algorithm that works over 1 millisecond. Well, you need to be able to have that sampling rate that enables it to. 1.5 megahertz is 1 millimeter resolution, that speed. And that's the minimum speed at high rates. Imagine if you go faster. I put another example here. One that's a bit less high rate is the aircraft you see on the bottom right. Just after a lightning strike, we also talk about ballistic impact. You have a UAV that you want to, a bit like a missile, make decision either you auto destroy or not because it's not working as supposed, it has been shot. Then you need to be able to make a decision fairly fast. Airbags. Suppose that you want to do a adaptive airbags inflation based on some feedback from acceleration and the weight of occupants. Well, you could do that through those high rate algorithms. So that's another example of high rate that we've done in a lab with the Air Force. So essentially what differentiates those systems from others is that we have 3 key challenges that are combined. The first one, if you imagine those missiles and some of those large uncertainties in external load, right? You don't know what you're going to go through. You don't know what hits you. If there's a blast, you can't really understand the wave coming at you on time. And from that, those big events, there'll be a lot of disturbance, very heavy disturbance. You will incur damage and changes in dynamic systems, and that will generate unmodeled dynamics. So these are perhaps the most complex systems that you can estimate in life. However, because of the nature of the system you have, the requirements on accuracy are not that high, right? What you want is to make sure that you maintain operations. You want to make sure you maintain structural integrity. So you can't give up on accuracy to get some computational time. So that's this example is what we call a drop tower. I'll put a video here. So there's a canister right here installed here. You have the canister on the bottom. I just take to granted that you can see my cursor right here. Oops. I don't know if you guys, that needs to go away. Hang on. Okay. Let's go back to this. So we have a canister. That's canister right here. It has 4 sensors in it stacked over each other. The sensors are accelerometers. They're stacked and they're embedded in epoxy in one of those. Epoxy they use for missile systems, so very strong epoxy. And what we do is we put it in a drop tower and release it with some preload and repeat the test several times and see what happens to the system. So that's one test here. Trying to click my wrong screen. There you go. So it's fast. This whole thing occurred over about 0.25 milliseconds. I will repeat. On the bottom left, you see a typical time series. So if you guys like state estimation, even like time series modeling and prediction, that's a challenge. You need to be able to model what you see here. But look at this. We have 5 different tests, and that's just the beginning of the time series. We'll look at it later. 5 tests, but 5 very different time series, especially between test 1 and test 5. You see the peaks, the change, right? So if you do one test, you train or you learn on that first test, but it won't necessarily apply to the other test. And that could be caused by wires becoming loose inside the system, the epoxy cracking. We don't know. We look at the canister, it looked perfectly fine after the 5 tests, but nobody knows. So based on this whole challenge, what we're trying to do here is establish how fast can we learn. And that's kind of the purple unicorn. I won't tell you. I don't want to spoil it, but the conclusion of this talk is we still don't know, right? So we need to do work towards that. But what we're trying, where we're trying to work is, can we learn a non-stationary time series without any pre-training? Right? We're telling ourselves the system is so complex that we can really pre-train, or maybe, as you will see, we'll give ourselves some chances. Well, maybe we have a little bit of knowledge, but can we essentially learn almost everything from the edge? And that's just a comment I just said. We'll give ourselves some chance here, saying, hey, there's an opportunity. We have some bit of physical knowledge. Does that help or does that hurt? Intuitively, it should help, but how much does it help? And that's something we'd like to quantify as well. And merging these two together, we're going to start talking about physics-informed machine learning to be able to solve the problem of high-rate state estimation. And if we can do all this, then eventually, as we proceed, as we complete the research, then we'll come up with a high-rate state estimator. And once the state estimator, for example, is being able to tell you the stiffness change, right? Being able to localize damage and quantify it. Not just saying there's something wrong, but going to the point we can make some better decisions with the system. Just a tiny bit here of lit review, what has been done. There's been a lot of work in terms of sensorless controlled induction motor. That was one of the first early pieces of work where people have really wondered about state estimation in terms of speed. Talk about sensorless, so here we're looking at observers, but a few points in this table of comparison of work where people have tried different algorithms and compare speed of algorithms. So look here, so the first one I put there is 1995. Look at the speed, 73 milliseconds. It's slow, right? With respect to what I just showed you, where that canister went in 0.25 milliseconds. That was 0.25 seconds, actually, 250 milliseconds. But then as we move forward with time, better computers, better algorithms, then we're able to achieve sub-milliseconds capabilities. So some good numbers here, very impressive, 5 microseconds, 19 microseconds. And I'm not saying this is not good for the higher system, but the problem that we have is those observers don't really apply well. The adaptive sliding observer is based on physical modeling. And so we need to have some physical information to apply it. Lemberger observer is something that's based on linear systems, right? So it's quite far from what we have. But as we dug through literature, we saw that there was hope, and most of the hope was located in the realm of adaptive observers. And that makes sense, right? An adaptive system is one that can adapt to changes in the environment. And if we see non-stationarities, then technically we could come up with an observer that could adapt to that. So we're saying, well, okay, we need some sequential system. And that's without surprise. That's what we like to do here, real-time learning. So of course, we had to find this as a conclusion. And then we built this research program with a couple different sponsors as time progressed. But we spent some time about 3 or 4 years ago to define this high rate problem. So that was the first few slides I showed you. So where you say, what are the challenges? What do we need to do? And then we look at different sides of the problem. The first one that we looked at was, can we learn a time series on the edge without pre-training? So it's not really time series prediction, but more time series estimation. Nothing to do with state here. Just looking at a time series and can we learn it? And it is a big gap between learning a time series and saying there's damage and quantifying it. So a bit difficult. And then we'll move a step further and say, okay, let's try to inject physics into that to come up with a better observer. And then the other is to come up with those physics-informed fast state estimators. So I'll give you an example of that where we've merged these two together. And we're yet to develop this, but based on the knowledge and discoveries and the research, we will soon jump into a idea of predictive high rate state estimation. It's not about knowing state right now, but what is the state in the future in a few milliseconds coming to be able to make better decisions. Right? Time is an issue here, so we can predict the future a tiny bit. That's going to help us. If I know the blast is coming and I can give the system 0.1 milliseconds to react a little bit more, then that'll be very useful. And there's the overarching objective here. So at the end, if we put all this together, then hopefully we can have this high rate state estimator. On the top right, there's a figure where we stand in terms of research overall. I tried to put general algorithm in terms of learning speed versus system complexity. So usually if you have a very complex system to learn, you might want to drop the physics unless you do have time to model everything. And you're going to use database estimators, so you use machine learning essentially. And these are very fast estimators, but the problem is you don't really have a link between information and physics. That's missing. On the other end, you have the model-based estimators. These are made for physics, usually used for less complex systems, but that takes a while. Imagine that you have a bridge that you want to monitor and you want to understand the vibrations, where you can go back and find a model, change properties of the bridge until you match the data from your sensors. But that takes a while. But once you're able to do it, then you have great information about your system. You know what's wrong, you can quantify it and do prognosis. There's the hybrid estimators in between. So we're kind of like in the top right here. We have this very specific class of system where we have a high requirement on learning speed, but it's also a very complex system, right? So not many systems are in that bubble, but some are. We're trying to address that problem here. A few key collaborators to be aware of. So Jacob Dodson on the Air Force Research Lab. So he's the one that helped pioneering this whole field. A colleague at Iowa State, Chahu, who loves doing prognosis and machine learning. Former student of mine, Austin Downey at University of South Carolina, who has been very successful at getting grants in that area as well and pursuing work. And another former student, Jonathan Hong, that works for the industry, Raytheon, that do have some work in the in some pieces of weaponry. Okay, we're getting slowly into like the real information here about the research, but the this is how these things can come together. This is more of like a window of an idea where we can learn a time series and we have some physical input. How do we merge these things together? So essentially we have the measurement. We start with the measurement, the sensors. One thing we've been working on very early is called a variable input observer. So that's the idea of learning a time series on the spot as it happens. If we can learn it properly, then we can predict it, right? So we can jump right here afterwards saying we can do prediction, step ahead prediction. Again, that's not very useful if we cannot link that to physics. The only thing that we can do is, well, okay, I made a prediction, the data I predicted are wrong, but therefore something went wrong with the system. So we want to go a bit further than that and say, hey, there's a crack in your missile located at x equal 0.5 meter, whatever, right? So on the other hand, we work on fast physical model updating. So having some cheap physical models, easy to update, fast, not quite accurate, but at least fast. So that will give us that little leg of physics that we need to merge these two things together. So take prediction, physics, and then we can come up with damage assessment. I put a link here. That's physics. So if you do have physical knowledge, why not giving it to your observer to be able to accelerate convergence? So I will start showing you a bit of research in those areas. Key challenges you have to keep in mind is first is learning on the edge. That's important to us. That means no pre-training. And that's a problem you find in civil structures. It's hard to test a full-scale structure. It's very expensive. So if you do work in health monitoring, for example, like the example of the bridge with, you put sensors, but to understand the signal, you don't have the luxury to take the bridge in the lab, test it, do several damage type, and then try to relate sensor data to damage. So pre-training is difficult. Machine learning is a lack of labeled data. We will give ourselves a very tight computational time challenge once they're under 1 millisecond. So we call that sub-millisecond decision systems. And we're going to try to quantify computation time versus accuracy. So that'll be quite important. So top left here's a dynamic system that was built at the Air Force Research Lab. It's called DRUP-BEAR. It stands for Dynamic Reproduction of Projectile Ballistic Environments for Advanced Research. So that's something you'll see later in the presentation. So it's a cantilever beam, and there's a cart, and the cart is this thing right here. You see the wheels. The cart moves along the beam pretty fast. So that will change the dynamics of your beam. The cart is somewhat of a boundary condition that moves. So it will change the frequency as time progresses. It's also equipped with a little magnet here and a mass can detach while the test is ongoing. We will not use that in the presentation. We haven't used that actually in the test yet. There's no data we have about the system where the mass is being released. So you do have it in a schematic on the right. So we started work on we'll call it FAST model reference adaptive system on MRAS. So the way this works is that we do have the real model we call reference. So that's the beam as you see it. So we assume we don't know it. We take measurements. We assume we don't have any knowledge in the system. So we take measurements from that. There's a sensor, an accelerometer in the system. You see it right here. And we also have, on the other hand, a model. So what I call a cheap model for the system. So it's easy to adapt. Spring mass, right? Model this as a single degree of freedom, one mass K, one mass M, one stiffness element, one damping element, and that's it. So as we get measurement, then we update the physical model, the adaptive model until we achieve this agreement with the measurements, right? So we look at the estimation error and we update the system. So we do it a bit more detail here. The way we build this cheap model, we do borrow to the field of reduced order modeling. It's called here CREP, that specific algorithm. So with CREP, you take where the sensors are and you build a representation based on the sensor. And to be here a bit brief in explanation, you have one mass where the sensor is, and you link the rest with spring elements. You try to come up with properties in your state space matrix that would match the dynamic of your system. So we do that. The adaptation rule was based on sliding mode theory, so something very traditional, something fast. What's quite important here with those systems is the excitation we apply is not considered as persistent. So persistent excitation is one that can excite most of the main modes of the system, such that when you try to adapt the algorithm, there's only one unique solution that exists. So if your excitation is not persistent, then it won't work. You won't be able to converge to one solution. So to deal with that, we looked at what's called concurrent learning. And the way concurrent learning works is that you build a vector of measurements. That's what would select data. As time progresses, as you get a new measurement, you decide whether this new measurement is useful to you in terms of information. And if it is, then you put it in your vector of selected measurements and you remove the least important measurement in terms of information. So you carry this vector of information in your system that you feed into your algorithm. So we did some simulation to make sure that it works before we applied it to the system. We looked at a single degree of freedom toy example, mass stiffness damping, and we changed the stiffness at one time. Actually, we didn't even change the stiffness here. What we've done is say the stiffness is unknown. We asked the model to build itself to find what is the right stiffness. We compare here in blue and red in the first graph up here. Blue is without concurrent learning. You have the legend right here, blue. The blue is without concurrent learning, and the red is with concurrent learning. You can see that if we don't use that concurrent learning, the lack of persistence in the excitation is creating problem. We can't converge. So we're going to focus now on concurrent learning, the red line, and see how this, if you do use concurrent learning, you do converge right to the real stiffness value. And on the right here, so what I was telling you about, this vector, where you try to keep the information maximum in terms of the new input in your system. So what we look at, what we do is we look at the minimum eigenvalue of that, of a autocorrelation matrix built on that vector, and we try to select which better input can be used to represent the system. So you can see that as we give better information, then there's convergence to the right stiffness value. And so what happened if you use two different parameters? Here we had, I think, stiffness and damping. So damping is theta 2. Same thing, without surprise, it works a bit slower because now you have two values. Now here's the real thing. So we try on that drop bear, two tests. One was using static displacement. So we took the cart at various positions, left it there. So you have it on the top right here in the figure, in the table. And for each different position, we had different frequencies, and we hit the beam, created an impulse. Another one will be the next slides where the cart moves in real time. So we tested the algorithm. What is it? 20 tests, and you have a figure for each test. This is the stiffness result. We also did it for damping. I don't have it here. Works pretty much the same way. You can see in red those little figures, the estimation that converges to the reference value, the right value of stiffness. In blue, that's the convergence point. Something noticeable here is that convergence speed increases with the frequency of the system increasing. That's quite important. Something that I've yet to understand a bit better, but means that if you have higher frequencies dominating, then maybe, just maybe, the convergence time will be faster. Damping is not shown. What happens with damping is you converge. The problem is we don't know the reference point because we don't know the damping of the structure. So it worked. But there you go. You have stiffness and damping here. The estimation versus reference. Again, the reference is the real system. Estimation was the algorithm gave you. And we look at the final value with a bit of a variance in the results and compare with convergence time. So you can really see its convergence time decreases as the frequency increases or the position of the cart increases. Similar thing with damping occurs. And again, damping, we don't know the reference value because it's damping. It's hard to measure. But you can see that we do have stable estimation of damping. So here's the moving cart. Now we just go back and forth. And you see here this little U shape. This is the position of the cart as a function of time. So we've started at 0, go to the front of the beam and come back. And meanwhile, we have some impulses that excite the beam. So this very messy graph, the top right is the reference versus estimation for the displacement, Z1. There's a match. There was no match I wouldn't show it to you, right? But it works. So we're able to match the acceleration. But that doesn't mean much. Again, it's just signal. What we want to do is be able to detect where the cart is. That's our state estimation. The bottom graph is the error. You can see the error, some chattering every time there's an impact on the system, but it does converge right after. Top right, that's the impulse that we had with an impulse hammer. So when they occurred. And in red, on the bottom, this is the estimated frequency of the beam from the cart position that we estimated. So red is the estimated cart position if you want. There's a one-to-one map between the frequency that we estimate to the cart position. So this is that explained the graph there. So we're trying to match the black line using the red. And it works okay. I mean, it's not, obviously, like it's quite a big challenge that in real time. But what you have to take from this is a computational time here. So you get that sort of result. There's big spikes, especially at impulse. So big problem with accuracy, but it does converge. The computational time is about But if you look at the table on the left, depending on the size of your concurrent learning vectors, the size of the input in your system, between 10 and 50, computational time is about 95 microseconds. So we're on the sub-millisecond, so we achieve the goal here for computational time. But convergence takes more time. The convergence speed increases with J increasing, your vector of information increasing, but it comes to the cost of computational speed, right? It's kind of annoying, but that's the trade-off that you have. If the system doesn't converge fast, then you do lose accuracy. So that's what you have to gauge in the field. I mean, are you willing to give up that much accuracy to be able to be very, very, very fast in your decision making? So the observations on there, so we do have average computational speed of 93 microseconds, but some challenges we talked about, so large chattering and overshoots. These were caused, we think, by the instrumentation. We had a good accelerometer, but not a great accelerometer on the system. And if you use sliding mode control or sliding mode theory, you need to know the displacement and velocity states. And the way we've done that is simply integrating. You know that if you do that, you do accumulate a lot of error, especially if you don't have a very accurate accelerometer. So one of the goals is that eventually we'll go back with a better piece of equipment to be able to get better measurements. And here that little theta that adapts itself, assume aerodynamics. So maybe a better way to do that is assuming non-aerodynamics and see where that leads. And here a little side note. We did look at a cart, and I put it right here because we did work with Dr. Sadu here. So Western content here. So we look at that cart, and we, as a side project, we said, well, can we look at the Fourier transforms? What I just showed you is a time-based method. I love time-based. The problem with frequency is that it takes time to do a Fourier transform. So that's why we're trying to stay away from that. But we're still nevertheless trying to go back and go with MATLAB and see, well, how about the short-term Fourier transform, about the wavelet transform? Can we compare those? So we went in there, compared 5 different methods in the frequency domain. So B, the figure B here is short-term Fourier transform. Then we have the wavelet transform C, and then the Wigner-Ville distribution, and squeeze synchronous transform, SSD, and MSSD, the multi-squeeze. That's line of work that Dr. Seti does. I'll go too far in details. I'm sure that he's one of his students here, so I don't want to get, be wrong about my explanation. But essentially, the SSD and MSSD are a bit different. They look at the energy in the frequency domain and try to rearrange this whole time frequency plot to be able to focus on the energy. So anyway, we did that with the results of the cart, and we'll see what works best here in terms of convergence time and computational time. If you look at the table on the right, well, first let's get rid of J2. J2 is the energy, so how the energy is concentrated in your data, and of course the last two, these two techniques are made for that. So they work very well. So they were able to really pinpoint where the energy was. What we care a bit more in with respect to high-risk estimation is the estimation error, J1 and J3, the average computation time here. So you can see the trade-off. So the first two techniques fairly fast compared to the others, but the estimation error is a little higher, right? Quite higher. So this is the trade-off. We keep talking about speed versus accuracy. You can also look at the convergence time, how long it takes that little red line that you see in the graph on the left to converge the right value. These converge much faster, but it takes much more time to get there, right, with a computer. So there was some trade-off. Pretty obvious if you're quite intuitive with the frequency domain. But we did look at the card that was moving, look at the same matrix. And then look, because it's time-based, we did not look at J2 and J4 as matrix. And here the trade-off is, again, obvious, where you can have the estimation error. Sorry, here it's not about a trade-off. It's not the point here. What we're looking at is the estimation error versus computational time, and we realize that these first techniques they're pretty fast compared to the last three techniques that we looked at, and they give a decent estimation error of the system. So in that paper, we said, all right, If you want to do frequency domain, it's fine, but you have to use, just like time domain, cheap techniques that are fast, but yet will cost you accuracy. Okay, so we're getting a bit more in machine learning now. That's another topic that we looked at, although it came a bit before this physics-based modeling, but we look at modeling time series and learning time series on the edge. Everything started with what we call the variable input observer. So imagine you have input time series and you have output. You want to link that together using some machine learning. The argument that we made is that we should play with the input space. This time series is non-stationary. It's hard to model. So the input that you feed in must hide some sort of information. So we base ourselves on the embedding theorem that applies to stationary systems. And what that theorem says is that if you have an unknown system, like the one you have on the left, you can take a delayed measurement from a single state into the state. That's what you have in the middle. And you can reconstruct the phase space of that guy using a delay vector, nu. So that delay vector is a measurement y that is delayed at step k minus tau, 2 tau, so on and so forth, for dimension of p. So the point is, the embedding theorem tells you that for the right tau and d, the right embedding dimension and time delay, if you choose it well, then you can create this new phase space on the right using that data that will have a one-to-one map between the unknown system. Getting that map doesn't matter to us, but what is key here with that information is that if you can find that nu, that nu preserved the essential dynamics of the system. And if it does, then you can use that as an input to your system. If you use that as an input to your neural network, for example, then you do feed your neural network with useful information. It's better than useless information, right? So the convergence speed will go up, and that's our secret sauce here. We're trying to use this embedding theorem to accelerate learning. And this is how it works. If you put it in a loop, we have just classic single layer wavelet neural network right here. So this thing of nodes, input, output on the left, output on the right. If you never seen neural network, think of your black box. It doesn't matter what you have in the middle. We use a wavelet neural network in that case. But the input that goes to it changes as a function of time. It's not just a single type of input. It's really, we build that every time. So we sometime we might have the acceleration of time t minus 10, and another time t minus 55. Right? So the type of input will change. And again, it's to characterize the time series a bit better. So as we progress, what we do is we have some signal, could be the output as well. And the algorithm here will decide, we'll look at the topology, the topological space of the time series, say, well, maybe this tau equal 5, d equal 3 is better. And it's going to recommend an input space. And then that goes in the neural network, estimation, adaptation. It goes back, said, oh, maybe we need a new input vector. Keep going on and on and on and on and on. So working on. We tried it, again, no pre-training. Here's the drop tower again. So essentially we have two types of tests that exist in a high rate right now. This is drop tower and drop bear. So we go back and forth between both. But the drop tower here, we have, we use two sensors. The one at the bottom we call time series 1 or TS1, and the one at the top called TS2. And you look at the time series at the bottom, they are different between T1 and T2, TS1 and TS2, different dynamics. So we try to train, not to train, but to learn in real time TS2 using TS1 as input. That was the main challenge. Look at this. Hey, it worked. So we have here, let's see, the gray line is experimental data. And we look at different way of adapting the input space in that particular paper. The smooth transition, the blue line, is what we're going after. We compare against a slower transition when we look at changing input space at different time as time progresses. Fast transition, we do every time step, and we just give the right input space every time. So it's kind of more aggressive transition to the right input space. And fixed is just a traditional fixed input as we do. We did a brute force approach where we look at 400 different type of input and say, this is the best. And we compare the data. As you can see, the blue line does a better job than any others, especially against fixed. So it shows that if you have an uncertainty system, well, adapting the input space to it is good. It's a good thing. And again, I won't get lost in details, but other techniques have some spikes. But here, the argument is that it's possible to learn in real time. And we did look at including physics. We asked MATLAB to come up with a 6-degree of freedom approximation time series, give it to us, and we start with that. We try to model the error instead. So we say, just suppose we know a 6-degree of freedom in our representation with this guy. Can we do better? It's called a hybrid approach in this case. You can see in the figure, especially on the right, we do much better. Right? The convergence at the beginning is much faster towards that gray line. So including physics, in that case, did great. So I'm about to show you a new technique that we're working on. This hybrid VIO will be a baseline for performance. We're going to say that this is the best that we can do. And we're going to also compare against the VIO. Well, before I move on, maybe it's important to mention problems with VIO. Well, two things. First, computational time is huge. It's big because of those little topological investigation you do at any time step. So that was not very applicable in real time. Another problem is that if you do always update the architecture of input space, you will never converge. The architecture of the neural network will never converge to anything. So you can reuse that for prediction. You can reuse that for estimation as well as a stable system. So we need to come up with a more stable architecture that could learn. So we came up with this idea using multiple recurrent neural networks in parallel. And the way this works is that each RNN will sample at different speed. So each RNN will have their own daily vector mu, and they're each going to try a different daily vector, and maybe one of them will get it right. Maybe a summation of those will get it right. So you have here that little time series that we sample at different speed. Each RNN have their own daily vector, and then as we move forward, we add the information each RNN spits, and that becomes our estimation. So I came up with that idea, did a bit of quick coding to see that would work. That's a nice little video. So what you see here is 4 RNN arranged in parallel. The bottom plot is the weight of the RNN as we move forward. We assemble them together. On the top is just a tracking error that occurs. And something interesting is you see the weight change depending on the type of dynamic. And I'm just going to move it a bit forward here. I'll pause it. So you can see that, for example, the black here, that's LSTM1. So each RNN has a LSTM cell. So you can see this guy jumping whenever you do have these higher chaotic events that occur. And conversely, the green one tends to adapt a bit later to those other pikes that exist that are just going downwards. Right? So we're able to demonstrate here that, look, okay, if we use many RNNs, some of them will adapt to different dynamics in the system. So great, let's formalize that. So we built this guy. It's pretty much the same graph as before, just rotated it 90 degrees, but you do have each RNNs that are arranged in parallel. This parallel computing help us gaining computational speed. Great. Each recurrent neural network is a long short-term memory cell, short sequence to make sure that it's fast at computing. Again, this hybrid problem. We have the attention layer that assembles information, and then we have the output. And we do the adaptation based on the classic estimation cost. That's, the estimation error is squared, and we need to minimize that. Something important here versus work with a VIO is that we do tell ourselves we have one event that we can train on. So there's one event from sensor 1 that we have in our pocket. We're going to train on that, prepare a network, and then we're going to try to estimate the excitation LS2. TS2 as time progresses. So there'll be some on-time learning, on the edge learning, but we'll give ourselves a chance. We'll say, okay, I do have this time series in my pocket. I'm going to pre-train a tiny bit, just get a step towards the right estimation. It's not the right dynamics, though. As you've seen, dynamic from TS1, TS2 are pretty different. So we use transfer learning to extrapolate to that new world. And yeah, again, this same slide seen before, both time series data. This we train using test 1 from TS1, and we validated using test number 1 through 5 from TS2. That's what TS2 looks like. I show you that at the beginning, just to show what those high rate systems were like, but you can see that in both figures, especially to assume that you have them left and right, each test is a bit different. So this is a challenge there in terms of learning. So when we design this recurrent neural network, we look at different number of RNNs, 1 through 9 as an example. The way we chose tau for each of them, we look at the topology and ran an autocorrelation test to see what kind of mutual information we have amongst different time delay. Top left is this kind of visual approach to this. So you have this phase space with tau equal 2 right here. You see the phase space unfolds, unfolds, unfolds as we increase tau. And as we reach tau equal 22, it's quite unfolded. And as we keep increasing, you don't have it there, it's going to fold back on itself. So we say, well, tau equal 22 is perhaps the small one. So we're going to be around that range and maybe underneath that. To find the dimension, the embedding dimension, we simply did brute force here, look at all the possible embedding dimension, doing the pre-training on TS1, chose the best one. So the bottom, these are just different architecture for 9 different RNNs that we're going to run through. The 5 RNN is what we started with all the simulation, and then we started doing a parametric study for a different number of RNNs. So this is for 5 RNNs, different tau. So when we do a pre-training, you can appreciate that for different tau, you have different information you pre-train on. Tau equal 2 is, the information is pretty naive. That means that information you get at time t is pretty much equal to t minus tau, right? Especially at high rate. So you do look at higher chaotic events. And as you move forward for t equal 14, then you do have a lag, an important lag. You look at more lower frequency content, right? You do see this kind of attenuation that occurs in the prediction that you have. So I'm going to try to assemble those 5 guys together that will learn the excitation of the edge. Now I'm trying to wrap this up to leave time for a question here, but results very briefly. So we did, as promised, I'm comparing what we've done here, the red line, this deep learning approach with the VIO in blue, and the hybrid approach that I claim is the baseline, the reference. And if you look at the beginning here of the excitation, like the blue lines, sorry, the red line beats the blue line in terms of speed of adaptation at the beginning, so it goes a bit faster, probably thanks to pre-training. Does not do as well as a hybrid VIO. But if you look also at peak events, right, the blue is way behind here. Same thing here. So there's a better adaptation to chaotic events just because we use different tau values and different sampling strategies. The bottom figure is just simply the error. So if you didn't trust what I just said, we have it there plotted where the VIO has high error and the assemble of RNN is quite lower and resembles a bit more the hybrid VIO. So we did look more formally at the hidden states, see if some of the RNN would adapt better to others. On the top, you have the attention weight, on the bottom, the hidden state. So I think what's more fun in this talk is talking about the hidden state. So for hidden state 1 and 4 in the LSTM, the blue one, hidden state 4, does not do anything, does not adapt when the excitation is somewhat stable. So good. Conversely, the red one did, right? So the hidden state 1, RNN1 was more sensitive to those more stable excitation. If you look on the other end, when things are changing a bit more, the blue one tends to, it's pretty hard to see here on my laptop, but yeah, take my words for it because I think it happens right here, but the blue one does adapt more than the red one. So the RNN number 1 was one that was more responsive to those more chaotic events. Spider plots, we like those to show the error. 6 matrix here, computation time, maximum absolute error, root mean square error, so on and so forth. The delay ratio tells you how naive the algorithm is, which means like how important the past signal was. So if If your estimation looks very much like the past measurement, then it's pretty naive algorithm. It's going to say, well, what I have seen now is what I've seen yesterday. And that's bad. That means it's not much learning. So I want to minimize J6. So first, let's look here. This is what I just showed a graph in terms of spider plot where we compare the VIO versus the assemble of RNN, so our strategy, and the hybrid VIO. And you can see there's quite a big reduction here in the error. We didn't look at computation time because the VIO would lose, obviously, so that wasn't very fair. And also quite a bit of a gain in the naivety. On the left, we look at different number of RNNs assembled together from 1 through 9, 1, 3, 5, 7, and 9. And this is just stating the obvious. So more RNN we have, more gain we have on the error diminishes. However, comes at a cost of more computation, right? So again, that's the trade-off that we always try to chase. So if you look at the root mean square error, J3, for example, for different RNNs, this decreases, right? And these are different RNN, different 5 tests, all the 5 tests. So it keeps decreasing, but the computation time over each test, test 1, 2, 3, 4, and 5 increases. So yeah, it comes at a cost. And the question is, are you willing to take a 60 millisecond computation time to gain a tiny bit more on the root mean square error? And that's depends on the application. So that's the last slide on the results here. We did look at the noise in the system. So what if we train on a signal that's noisy, a different signal to noise ratio? And we, through this particular example with the drop tower, well, we discovered that this was robust up to signal to noise ratio of 20 decibel. Again, 5 plot, 1 for each test with TS2. And to say that could work with some level of noise, but there's a point where that thing won't be good anymore. So overall, good performance. We approached the hybrid VIO strategy. Very, very, very fast computation time, 25 microseconds with 5 RNN. But we've seen a lot of chattering. I didn't show it to you in the slide, but there was some chattering when the excitation is low. But yet we came with something robust, essentially. This is what we're at right now, trying to do. So just based on this conclusion, again, I'm trying to gain a bit of time here to enjoy some questions, but we're trying to work on faster adaptive models to get some physical insight. Like I said, figure out what is the problem with those measurements, so those instruments that we use to take measurements. Can we do something more accurate? It's a better way to get to the displacement velocity state. Look at nonlinear dynamics. And that's what we're going to merge with the step ahead prediction in order to be able to make assessment and decision making. And in terms of deep learning, what I just showed you, we're trying to move towards the idea of splitting that time series into more defined multi-scale event or multi-rate event. So having something that really formally look at lower frequencies, while another RNN will look formally at higher frequencies, while staying in the time domain. So we're trying to investigate techniques like those. And of course, we're bridging everything together by building this hybrid we call context-aware state estimations. If we feed in more information, more metadata type information to be able to converge faster towards states, right? So if we know that something failed on a missile, is it very likely that's going to be the head of the missile, for example, right? Or something like that. And of course, what's very important is the decision making. I always like to talk about this when I teach structural health monitoring. You have measurements, but you need to be able to make decisions with it. And that's a big gap right now. So a lot of work towards that. But if I tell you the bridge cracked, is that important? And what do you do about it? And these are the sponsors that make this happen. So we had the Air Force, FOSI, FRL work together, and the National Science Foundation, where we're trying to work on hardware to enable those fast learning algorithms. And ARA's Applied Research Associate is quite a big private research firm in the US that do work with the FRL. This is it.
Thank you very much, Simon. Very interesting. So I would ask anyone who has questions to, you can turn on the video if you want, but please just unmute yourself and ask the question. So this time our chat window is not enabled, so we'll take care of it next time. But I just have two quick questions, probably quite naive because it's not my field. So in the domain you're focused on, very short time intervals, and you give the examples of blasts, etc. Is it also applicable for natural hazards like tornadoes, etc., affecting the structures, or the frequency for those events are still quite large compared to what you're doing?
It's a good question because we did think about it, and we're still thinking about it. There's some events where that could be applied. Seismic, for example, right? If you look at a seismic wave, it travels fairly fast in 1 millisecond. Mm-hmm. So can you learn from buildings that already seen the wave and they tell you, hey, yeah, something's coming? So that could be a good application. Mm-hmm. The wind is a bit slower in terms of high rate, but nevertheless, you can still have this learning system. Know the tornado is coming. Some physical system experienced the tornado, and can you really learn from that? Mm-hmm. And we did have a major event in Iowa with wind a few months ago. It's called the Redshift. It's an inland hurricane, essentially just in a straight line, and we had no warning for that. Nobody could tell us it was coming. It came at 70 miles per hour, and that's fast. And winds were like 130 miles per hour, so I think they're pretty damaged. These are systems that could benefit real time. Yet, we're not talking about some millisecond. If somebody would have told me in a few seconds, that would have helped. I would have stayed inside, but yeah.
Yeah, and thank you for this. When you use these RNNs, what is the basis of the different structures or topology you mentioned for defining, or to define those? And do you just do you take a simple average, or what? I think you do the weighted average, something like that. How do you find the weights for each of those models?
So the RNNs, each RNN, we try to think of them as an individual machine learning tool, neural network, and we like to think of them as learning different part of them, so different behavior, different feature. So we build this different topological input. One would be more aggressive, where we look at closer data, and one will be less aggressive, so more like low frequency if you want. So they're all trained based on that first time series. And the way we find the weights when we assemble, that's the learning process that happens in real time. So that way, when we apply the transfer learning, we try to minimize the overall error. So these will be the hidden states that you've seen, some of the other associated with weight, essentially, and more or less. And then you see them adapting to different features in time series. And this adaptation gives rise to the weights that we're going to find at the end. So there is another neural network involved in that, in discovering the weights.
Okay. Yeah. Okay. Thank you very much. All right, I see that Shuhang has raised his hand. Go ahead, Shuhang.
Excuse me, I don't have a question related to the project. I just want to know if the attendance constant is finished, because I have a meeting following at 2:30, and this is kind of a bit longer than I expected. So I'm just kind of wondering about this.
Now that you ask, I'll take another attendance just quickly, and then you can leave afterwards.
All right, thank you.
Yeah.
Is that finished?
You can leave. Yeah, it's
all
after
right,
2:30, and yeah.
Yeah, thank you so much.
Yeah, no problem. All right. Because I don't have all the participants on my screen, you can raise hand or just unmute yourself to ask the question. Probably Dr. Sathu's students are here and they have some highly technical questions.
So how many students?
Go ahead. I got a question. I'm from Dr. Sadhu's group. Have you looked into using, I know that typically our RNNs, they're typically trained methods. So as you said, that they require a lot of labeled data and stuff. Has there been any research done into semi-supervised or unsupervised methods, such as generalized adversarial networks or anything like that?
We have not looked at that. So it might come, but we start with RNNs based on the idea of that the VIO worked.
Okay.
So the VIO was promising with single wavelet neural network. So okay, the RNNs are a better architecture for running time series to start with. So I think it's quite intuitive. Usually, if you do look at time series, you put RNNs, and we say, well, okay, it's non-stationary, so let's add some memory to it. So we integrated that with the LSTM architecture. Again, we kept short sequences to make sure it's fast, but we haven't looked at other type of machine learning that may come, but I think our main interest right now is to be able to bridge towards predictive step ahead prediction. And that won't happen unless we can actually control very well what kind of features each RNN will be trained on. But they're not what we'll build there is not a pure on the edge learning algorithm. There is some supervised learning involved because we do train each RNN based on that first time series that we assume we have with us.
Yeah. Okay.
All right, excellent. Thank you very much, Dr. Laflamme. Very interesting talk. We are well over our time limits, so I think we can stop it here. I thank everybody for attending this interesting talk, and I hope that in our next series we will have in-person presentations from you after this COVID situation. Thanks again.
It's a pleasure. Thank you.
Yeah, thank you, and have a wonderful rest of the day.
Thank you as well. Thank you.
Thank you. Bye-bye.
Hi, Professor.